So last time we saw finite volume method. So we had this integral conservation law from which we started to derive the finite volume update formula. That is to have conservation inside each cell. We started with the integral form and then we obtained an update formula. So that will help us to have discrete conservation, that is conservation inside each cell. And then we talked about reconstruction of fluxes. So in finite volume method, we'll require fluxes at the interface, whereas we store the values at the cell centers. So we somehow need to construct the value of U and G at the interface. G I mean as by G I mean flux. Okay, U is the conserved variable. So since values are stored at the cell centers, we need to find some way to evaluate G at the interface. So that is one problem called reconstruction. So that most of the finite volume methods are developed based on how we reconstruct the fluxes at the interfaces. So this is one thing. And then we saw about upwinding. So last time, you know, we saw reconstruction, and then we just saw that if we use FTCS scheme, that is if we use uh, if at the interface, if we take half of the value from the left side of the interface and half from the right side, that is if j plus half is the interface, then j is the left side and j plus 1 is the right side. So these are cell centers, j and j plus 1. So if we take half of G from the cell center of left cell and half of G from the cell center of right cell, and make that as the value at the interface, then we'll get an unstable scheme, which is unconditionally unstable. So whatever condition we put, we cannot make the scheme stable. So there is no use of solving this scheme. So we tried upwinding. We told that there can be two ways to overcome this. One is adding numerical diffusion, the other one is upwinding. So last time we saw this addition of numerical diffusion. When we add numerical diffusion, we get a scheme that is stable. So we sort of get a convection numerical diffusion equation. So this is the numerical diffusion part that we have added. So this is it. And then we also saw some gist of upwinding last time. So we did Courant splitting. This is for only linear convection equation. Today we'll see how to do upwinding for any general nonlinear scalar conservation law and also for systems of conservation laws like Euler's equations. So today we'll see all that. So this is upwinding for a simple linear conservation law wherein we did Courant splitting. That is, this variable C can be split up into positive and negative quantities. C plus will always be positive and C minus will always be negative. And then we can use this C plus plus C minus in place of C. And then for the contribution from C plus, we can do backward differencing in space, and for the derivative contribution from C minus, we can do forward in space. So that way we get pure upwinding. So this scheme also introduces numerical diffusion. So and then it becomes stable. We have some stability condition for this upwinding, which is mod C delta T by delta X less than or equal to 1. So for this kind of upwinding, we get a stability condition, and if we satisfy that condition, our scheme will be stable. So we saw these things last time, and we also saw discrete conservation thing. So today we'll see more of upwinding. So for a general linear scalar conservation law, where c is the wave speed. So here this is our scalar conservation law. U is the conserved variable and Cu is the flux. So this is in conservative form, this is in non-conservative form, and for for linear conservation laws, there's no difference between conservative and non-conservative form, because C is just a constant. It doesn't matter whether it's inside or outside. So it's both same. If it's non-linear, then if g of u is a function of u, then we need to, this is in conservative form and this is in non-conservative form. Here we just do dou g by dou u into dou u by dou x. We just do chain rule. Both are equivalent only when g is differentiable. That is dou g by, only when dou g by dou u exists, these both are equivalent. Otherwise, these two cannot be equivalent. Here we have implicitly made an assumption that dou g by dou u exists. So this is in non-conservative form. So let us first look at the linear conservation law. So for linear conservation law, this is the way we did upwinding. We've actually split C into positive and negative quantities. C as C plus plus C minus, and C plus is C plus mod C by 2, and C minus is C minus mod C by 2. So that way we have done backward differentiating for the derivative corresponding to C plus and forward differentiating for the derivative corresponding to C minus, because if C is greater than 0, things are coming from left to right. So I will be influenced by I minus 1, and if C is less than 0, I will be influenced by I plus 1. So in the first case, where C is greater than 0, we do backward differentiating, and for the second case, when C is less than 0, we do forward differentiating. So this is the essential gist of upwinding in the basic thing that is followed in upwinding. Let us now look at nonlinear conservation laws. So in this case, how do we do upwinding without going to non-conservative form? Because in finite difference framework, we do upwinding in this way. We put the equation in non-conservative form and we see the value of dou g by dou u. Let's just call dou g by dou u as a of u, and then let's just do Courant splitting here. We'll split a of u as a plus and a minus. So that is this equation. So you based on that splitting, we do the finite difference. We do upwinding in finite difference framework essentially. So this equation is actually rho u by dou t plus a plus of u plus a minus of u into dou u by dou x. So this is equal to 0. This is our equation. So we do forward differentiating for this and backward differentiating in space for the derivative which comes due to this quantity a plus of u into dou u by dou x, and for a minus of u into dou u by dou x we do forward differentiating. So that's what we have done here and we have gotten this equation. So this is our update formula in finite difference framework. Now how to do it in finite volume framework is our question. So we cannot just consider this non-conservative form and go about doing the upwinding. In finite volume framework, we actually started with the integral form of conservation law. So which is essentially this conservative form with an integral over the over the domain, either the cell or the physical domain, whatever. I mean, here in the finite volume framework, we are doing this integral in each cell. So omega here represents just a cell. So this conservative form will be integrated. Okay, this is now the integral form. When we integrate this conservative form, we get the integral form. So we essentially start with the integral form of conservation law in finite volume framework. So it's just an integral, right? We can differentiate it back again with respect to the domain and then get back the conservative form. So it's okay to either start with integral form or conservative form in finite volume framework. But we cannot just start with this non-conservative form, because here we are inherently making this assumption that dou g by dou u exists. So we need to either start with integral form or conservative form in finite volume framework. So in that case, how do we do upwinding? So here we don't see any wave speed separately. Here, how do we do upwinding for the flux? So that is now a major question. So suppose if we can write g of u as some k into a of u into u. A of u here is dou g by dou u. So, and k is some real number. Suppose if we can write such a thing, then what happens? So until this, is it clear? I mean, is there any doubt in why we are using conservative form for starting the finite volume method?
No, no.
Okay, fine. So now now that it's established that we are going to take a conservative form for finite volume framework, so now let's just take that for granted. So now we need to do upwinding for this equation. So in this case, we don't see the wave speeds, and it's doing upwinding over here is not direct. So to understand how to do upwinding for this, let's see the following. So if we assume that we can write g of u as k into dou g by dou u into u, where k is some real number, then g of u can be split up into k into a plus a minus into u. A of u can be split up, right? A of u is some number for which we can do Courant splitting. Like this will be a of u plus mod a of u by 2, and this will be a of u minus mod a of u by 2. So this way a of u can be split up into positive and negative quantities. So we are substituting that split up over here, and then we can separate this. G of u can be k into a plus into u plus k into a minus into u, and this first part will be g plus, and the second part will be G minus. So here we have achieved some flux splitting. So G can be split up into G plus and G minus. G plus is the positive flux and G minus is the negative flux. So now how to put that in our finite volume update formula. So that again is another question. So we have now seen that how we can split any flux into positive and negative quantities just by this assumption. Only if this assumption holds. If we have some kind of flux where this assumption does not hold, then it's not possible for us to split the flux into positive and negative. So let's now see how to evaluate the flux at the interface. Right now we have seen that these are actually quantities at the cell centers. We in finite volume framework we only store values at the cell centers. If we know value u at some cell center, say L or R in this picture, so we know value u at both L and R, so I have UL and UR. So using that I can find G of UL, because G of u for inviscid Burgers equation is half u squared. For some other for linear convection equation it's Cu, and so on. So it's just a function of u. So since G of u is a function of u, in that function if I substitute u as ul, then I'm going to get G of ul. So I can evaluate the flux at the cell centers. Both G of ul and G of ur can be evaluated. But how do we evaluate the flux at the interface? So this interface is now Ri. So how do we evaluate the flux at GI, flux at the interface I? So to do that, let's see how we are doing it. So the flux at UL will be split up into G plus at UL plus G minus at UL. Similarly, flux at UR will also be split up into G plus at UR and G minus at UR by the same method that we have discussed now. By this assumption, we can do this splitting. I mean, this can happen only at the cell interfaces. Now, how do we use it to evaluate the flux at the interface? So, the positive flux from left side goes in this direction. So, towards I, and the negative flux from L will go in this direction towards the other interface. Similarly, negative flux from R will come in this direction. It is this green point that I have drawn. That comes towards the interface I, whereas the positive flux from R will go towards the other side of the interface, other interface of the cell. So, in order to evaluate flux at this interface, you only need to consider positive flux from left cell and negative flux from right cell. So that's what we are doing here. That is this expression. We are just summing the positive and negative fluxes from left and right cell centers respectively. So that's what is happening here. So this is how you evaluate the fluxes at the cell interfaces by using the split fluxes. So now we can substitute these expressions in our finite volume update formula. So last time we saw how we obtain this finite volume update formula. So suppose if we do this control volume analysis for the cell, we get this expression. We essentially get d by dt of u bar plus d plus this thing. When we are doing it for the cell when we do it for this cell, we get this update formula. This is the integral form of conservation law, and when we do forward Euler in time, we get this. U bar is the solution average. We'll have some random value of u in this cell, but we find an average of that and we put that at the cell center. So that's what is u bar. So u bar at I. So I think this is something that we have discussed last time. So let's not get into that. So now let's take this finite volume update formula for granted. So we have this expression. So in this expression, thing, uh, things are actually stored at the cell centers. So we know values at I plus 1 and I minus 1. And for gi plus half and gi minus half, we need to find some way to evaluate them. So that's what we did as of now. To find the values at interfaces, we have found an expression. So now let us substitute this expression over here and here. So based on this expression, our gi plus half will be gi plus half is this interface. So it will have a positive flux contribution from I and negative flux contribution from I plus 1. So that's what that expression is written over here. And similarly, flux at the interface I minus half will have positive contribution from I minus 1 and negative contribution from I. So that's what is written here. So now let us use these expressions in place of gi plus half and gi minus half in the finite volume update formula. So then we get such an expression. So actually I've just substituted it. So now if you look at it, we can just separate these terms, just rewriting this in this form. We get a backward differencing in space for our positive flux and forward differencing in space for our negative flux. So this is similar to what we got in the finite difference framework. The difference is that we are not we are not actually putting the equation in non-conservative form and identifying the wave speeds and then doing upwinding based on the signs of wave speeds. We are essentially looking at the flux itself and we are splitting the flux as positive and negative. Instead of splitting the previous case, wave speeds were split up and by looking at the wave speeds, we did upwinding. But here in the finite volume framework, we are splitting the wave speeds as well, but because of this assumption, wave speed splitting will lead us to flux splitting because of this assumption. So then we are doing upwinding based on flux splitting. And all of this was possible only because of this assumption. So now what this assumption is. So, and can this assumption be true all the time? So for linear convection equation, we have g of u as cu, and here c is some general real number, and we have our a of u, that is dou g by dou u, as c. And here you know, this C of u, G of u can now be written as some a of u into u. Since C is a of u, in place of C we can substitute a of u and we still have this u. So G of u can be written as a of u into u. So this is exactly this expression with k equals 1. So now linear convection equation satisfies this property. Now let us look at Invisible-Burgess equation. So here again, g of u is half u squared and a of u, which is dou g by dou u, is u. And now this half u squared can be split up into half into u into u. So actually we cannot write dot over here because we don't have vectors, so they are just scalars. This is actual multiplication only, scalar multiplication only. So we have half into u. So let's just substitute u is a of u. So for one of the u's, let's just substitute a of u here and let the other u remain as such. So now this g of u equals half into a of u into u is of the same form as g of u equals k into a of u into u, where k is half. So we now get the same form that we assumed for Invisible-Burgess equation as well. So and let's just consider any g of u with some non-zero integer power. So let's just say g of u is c into u power n, where c is some real number and n is a non-zero integer. So it can either be negative or positive. So now in this case, a of u will be dou g by dou u, that will be c into n into u power n minus 1. So now let us just write our g of u as c into u power n minus 1 into u. So in that case, c into u power n minus 1 is a of u by n, right, from this expression. So that way we can write g of u as 1 over n into a of u into u, and this will just remain as such. So now this is also the same form that we assumed with k equals 1 over n. So for certain kinds of functions, certain kinds of g of u, this assumption holds true. Let's just say that c of u is a trigonometric function now. So g of u is c into sine u, where c is again some real number, and a of u is dou g by dou u. So that is now equal to c into cos u. So now can cos u into u give us sine u by some means? Is it possible? So is it possible?
No, ma'am.
Yeah, it's not possible. So here we cannot write g of u as k into a of u into u. So this is not of the form that we assumed. So this assumption will hold true only for certain functions, certain functions of g. Certain functions, certain g of u, which are functions of u. Actually, g is some u into r. G is a function from u into some real number. So this thing actually holds for some specific forms of G. So now let us see what some property known as homogeneity property and how this property will lead us to having that assumption. I mean the assumption G of u equals k a of u into u. So how this property will lead us to that assumption. So that's what we'll see here. So now consider some general function f of x. So this is nowhere relevant to the domain that we are in right now. We are in u and g of u part. So this is completely separate from that. We are here now. We have the variable x and our function f, which is dependent on the variable x. So the domain is completely different, but the inference that we get from here will be used for this. That is, the inference that we get from these variables will be used for these. Okay, so now suppose if let's just ignore this blue k. Everywhere I have marked a blue k, we'll come back to that later. So now let us just consider this white part of the equation alone. So consider some function f of x and some scalar m. So suppose if we write if f of mx equals m into f of x, then we call f of x as a homogeneous function of degree 1. So what this is some definition, okay? So if this property is satisfied, then f of x is a homogeneous function of degree 1. So if this happen, if this property is satisfied, what happens? So that's what we see here. So let us just differentiate this equation with respect to m. So that is what is over here. So I've differentiated this equation with respect to m. So now the right hand side gives us f of x. Dou by dou m of m into f of x will give us f of x. And the left hand side will give us something like this. First of all, we do chain rule. I mean, f is a function of mx and we are differentiating with respect to m. So first let us differentiate this whole f with respect to mx only. And then let us differentiate mx with respect to m. So this is just chain rule. Usually we have the habit of writing this mx as some other variable w, and then we'll differentiate f with respect to that variable, and we'll differentiate that new variable with respect to m. So this is the same chain rule that we regularly do. So this is what we get now. And this dou by dou m of mx will give us x. So in that case we have this expression. Since we have assumed that m is any scalar, right? So m belongs to the set of all real numbers. M is any real number. So the whole of this thing argument holds when m is any real number. So we can, since it holds for any real number, it holds for 1 as well. So we can take m equals 1, and in that case we have this expression. We have dou by dou x of f of x into x equals f of x. In this part we have just assumed m as 1. It's not assumption, we have just taken m as 1. This holds for any m, and we have just taken this, written this expression for specific m equals 1. So now we have gotten something, right? So this is equivalent to the assumption that we made earlier. Initially, what did we make? We made g of u equal, we made this assumption, g of u equals k into a of u into u. Here a of u is actually dou g by dou u only. So this was our assumption that we considered in doing upwinding. So this assumption is derived out of this. So now this equation is equivalent to taking this assumption. Let's just replace f by g and x by u. We get this equation. Ignore k here right now. So we have dou g by dou u into u equals a of u into u. So this will from this right hand side we get equals g of u, and from this left hand side we get this. We have essentially gotten this dou g of u equals dou g by dou u into u. As of now we have not gotten this k. So this is something that we obtain out of this homogeneity property. Now let us suppose that we have this property. If k into f of mx equals m into f of x, if this is true, then what will happen? In that case, we again in all these steps we'll have a k in the left hand side of the equation, and on the right hand side we won't have anything. So I just added k everywhere. So here also in the left hand side of the equation we have a k. So now this gives us something like this. In that case we'll have Since we add k only to the left hand side of the equation, we get something like this. So this is the assumption that we made earlier. So this in this way, upwinding for scalar conservation laws is done in finite volume method, and yes, this will hold only when our fluxes in the conservation laws satisfy this property. Certain types of fluxes will not satisfy this property, and for such fluxes we cannot do upwinding in this manner. We'll have to work more. I don't know if some research has been done on doing upwinding for other kinds of functions. So as of now, let us just consider only the functions that for which this property holds. So let us now consider only the functions for which this homogeneity property holds, and for which we can get this inference g of u equals k into dou g by dou u into u. So we'll be considering only such functions. So as of now, we have seen how to do upwinding for scalar conservation laws. So from the beginning, we have considered a linear scalar conservation law where u is a scalar and g of u is also a scalar. Here g of u equals cu for our linear scalar conservation law. So this is also a scalar. And also even we saw it only for nonlinear scalar conservation laws where u again is a scalar and g of u is a function of u, and it's also a scalar. In that case, we saw how to do upwinding. So now let us move for systems. So for systems of conservation laws, I am using capital letters here for systems. So we have dou u by dou t plus dou by dou x of g of u equals 0, where u is a vector consisting of many scalars from un up to up, and g of u is a vector consisting of scalars g1 and g2 and up to gp. Here each of these g1, g2 are functions of this whole vector and not individual u1, u2 up to up. They are functions of this whole vector themselves. That is, you can depend on all of these values u1 up to up. It is each of these quantities fluxes g1 up to gp can depend on all of these u1, u2 up to, that is g1 can depend on u1 up to up. The same holds for all g's, that is g1 up to gp. All g's are dependent on all of the elements of the conserved variable vector. So now here p is the number of individual equations in our system. So this is our system, and in this system of conservation laws we have p individual scalar conservation laws, and but these conservation laws are coupled. Okay, each of them are coupled because I told you g1 is dependent on all of the conserved variables, not just u1. g1 is not just dependent on u1, it's dependent on all of the conserved variables all of the elements in the conserved variable vector. So yeah, that way we have a coupled system. Actually earlier when we were doing PDEs, we saw how to decouple a system. So we'll not get into those things right now. Right now we'll see how to do upwinding for systems of conservation laws. So we just have a system with certain elements, a system consisting of many number of scalar conservation laws, and that number is p here. We have it's a fixed finite number of equations are there in our system. So now for this system, what will be the finite volume update formula? This is in conservative form. So this will be our finite volume update formula. If we construct a domain, I mean if we have a physical domain and if we discretize the domain into cells, we can do this control volume analysis for each cell, and then we get back a finite volume update formula. So that's what is given here. So we have this finite volume update formula for each cell in our physical domain. So this conservative form of uh, the the continuous equation, conservative form of continuous equations has been discretized into this equation in finite volume framework. So for this, if we want to do upwinding, we'll require again the same arguments. So here again, to do upwinding, we cannot just write dou u by dou t plus dou g by dou u into dou u by dou x equals 0, and then by looking at the values of dou g by dou u, we cannot discretize dou u by dou x accordingly. We need to do this upwinding while staying in conservative form itself. We cannot go to non-conservative form and then do upwinding. So here again the same arguments hold. To do upwinding, we need to remain in conservative form in finite volume framework. Otherwise, we are losing the essential advantage of staying in finite volume framework. So we need to do upwinding while retaining the conservative form. So suppose here again the same arguments hold. If we can write g of u as k into dou g by dou u into u, and dou g by dou u here is a vector. I mean, it's a matrix. U is a vector, right? U is a vector consisting of p elements, and g is a vector consisting of p elements. So when you write dou g by dou u, you are differentiating each of these elements by all of these. That is, g1 will be differentiated with all of these elements, and g2 will be differentiated with all of these elements, and so on. So you put them all together, you get a matrix. So that is a of u as dou g by dou u. So that is equal to this matrix. The first row consists of derivatives of g1, the second row consists of derivatives of g2, and so on. So now if this matrix A of u can be diagonalized. So for diagonalization, we require linearly independent eigenvectors. So these are things that we saw earlier when we were doing PDEs. So to diagonalize a matrix, we require linearly independent eigenvectors. And we assume that our system has this property, that is, we have linearly independent eigenvectors for our dou g by dou u matrix. So the system that we are considering, the form of g of u that we have, satisfies this property, that is diagonalization of the matrix that we obtain out of G. That is, our G of u is in some form, right? So that form is such that dou G by dou u matrix is diagonalizable. So we are now making that assumption. So that way, whatever we do from here on will hold only for such systems of conservation laws where this property holds. But this property is not so stringent because it holds for any hyperbolic system of conservation. I mean, this property holds for hyperbolic systems. So the physical equations like Euler's equations will satisfy this property. Euler's system, that is mass, momentum, and energy conservation without viscous and diffusion terms, that system of equations will satisfy this property. So now we have made these two assumptions. Both are quite reasonable assumptions. So now let's just, I told that this matrix A can be diagonalized. So in that case, we can diagonalize in this manner. A of u is now R of u into D of u into R inverse of u, where R of u is a matrix whose columns are eigenvectors, are the linearly independent eigenvectors of A of u. And D of u is a diagonal matrix consisting of the eigenvalues. So now each eigenvalue can be split up into positive and negative quantities by Courant splitting. These are scalars now. Although these are functions of u, lambda 1, these are again functions of u. but these are scalars. So we can split them into positive and negative quantities by Courant splitting again. So since these are functions of u and u varies at different grid points, so their values will be different at different grid points. So at each grid point you do this Courant splitting and you split our eigenvalues into positive and negative quantities. So now you, based on this, you split the diagonal matrix. So in the first you split D as, since lambda I is lambda I plus and plus lambda I minus, you can substitute this over here for each of these diagonal elements, and then you can split this diagonal matrix into two. We can have the all positive quantities being as one matrix plus all negative quantities being in another matrix. So now this is D plus plus D minus. They are both diagonal matrices but with only positive, that is non-negative elements here, and here we have only non-positive elements. I mean, you're getting it right. So because of Courant splitting, we'll have this. So whenever lambda I is greater than 0, your lambda I plus will be equal to lambda I, and lambda I minus will be equal to 0. Similarly, whenever lambda I is less than or equal to 0, your lambda I minus will be equal to lambda I, and lambda I plus will be equal to 0. So here only there will be only positive diagonal elements will either be positive or 0 for the D plus matrix, and for D minus matrix those diagonal elements will either be negative or 0. These lambda 1 minus and 2 lambda p minus, they will either be negative or 0. So that way this matrix consists of only non-negative elements and this matrix consists of only non-positive elements. So now through this, first we have split the eigenvalues and then we are splitting the diagonal matrices into positive and negative. So now this diagonal matrix, I mean the full flux Jacobian, that is A of u, which is dou G by dou u, that can be written as R into D into R inverse. So through that we can now substitute D as D plus and D minus, and then we can obtain the splitting of A. Now A can be split up into A plus and A minus because we can substitute D over here as D plus and D minus. So we have obtained this splitting. Now the flux Jacobian itself is split into positive and negative quantities. So this is basically our dou G by dou U. That has been split up into dou G by dou U plus and dou G by dou U minus. So now we have gotten this. All of these has come out of this linear assumption that our diagonal or matrix A of u has linearly independent eigenvectors. So through that assumption, we have gotten all these inferences up till here. So now let us use the first assumption. G of u equals k into A of u into u. So using that, since we have already seen that A can be split up into positive and negative flux Jacobians, we can substitute that over here and then split G as G plus and G minus. So that way we have obtained the splitting of fluxes. This is similar to what we have obtained in scalar case earlier. So now this splitting of positive and negative fluxes has been achieved. So we can go about doing substituting these in the finite volume update formula. That is, first we need to evaluate the value of flux at the interface, and then we'll be using those values at the interfaces in the finite volume update formula. So this is something, this is same as what we have seen earlier. So if we have some cells, some number of cells, so this L is one, this is one cell, and this is another cell. So here L is the cell center, and here for this cell R is the cell center, and they are both separated by the interface I. So to this interface I, we get the fluxes from both left and right sides. From the left side, we only get the positive flux G plus of U, and from the right side, we only get the negative flux G minus of U. So we add them both and put it at the interface. So we get G of U at the interface as G plus at the left cell center and G minus at the right cell center. So that way, using the same argument, we can now evaluate, Gi plus half and G minus half for any general finite volume. We had this finite volume update formula, right? So we have Gi plus half and Gi minus half. So those values can be substituted here. So Gi plus half will have positive contribution from I and negative contribution from I plus 1. Similarly, Gi minus half will have positive flux contribution from I minus 1 and negative flux contribution from I. So now let's use these expressions in the finite volume update formula that I showed earlier. In that case, we'll get such an expression. Here we can evidently see that backward differencing is done for positive flux and forward differencing is done for negative flux. So this is now our finite volume update formula. We can use this to find the values at cell centers. Any doubts here?
No, ma'am.
Okay. So I think we have done upwinding. We'll move to further part next time. We'll have the next class. We'll see Steger-Warming flux vector splitting and Van Leer's flux vector splitting methods. So this is an essential gist of upwinding. So can we continue or can we see it next class? In the next class.
I'm ready to continue now, ma'am.
Okay, fine. So, yeah. As of now, we have seen upwinding in finite volume method. That is, we got some update formula. So where which is like ui bar n plus 1 minus ui bar n by delta t plus gi plus half at n minus gi minus half at n by delta x equals 0. This was our update formula, and all those u bars at I and I plus 1 were stored at the cell centers, and gi plus half and gi minus half were from the interfaces. So we somehow needed to evaluate those values at the interfaces by using the values at the cell centers. So for that, we just made certain arguments, and then we came up with the values for G at the interface through upwinding previously. And in the previous class, we made an argument about doing just averaging of values from both left and right side, and we got an FTCS-like scheme which was unstable. So that is why we went to upwinding, which only took positive flux contribution from left side and negative flux contribution from right side. That way, we got an upwind scheme. So that is basically upwinding. So now let us see some of the properties of numerical schemes when upwinding is done. So, let's again, we have seen some systems of conservation laws. Let's just forget it right now and come back to scalar conservation laws again, which we started with earlier. So for scalar conservation laws, I'm just considering a simple inviscid-Burgess equation. So this is a scalar conservation law, right? So where u is a scalar and g of u is half u squared for inviscid-Burgess equation. For any other equation, it will be just any other function of u. So we'll just find a of u to be dou g by dou u, and which is u, and then we just split this A of u as positive and negative quantities based on its sign. So we did Courant splitting and split this wave speed A of u, and then we made this assumption k into A of u into u property. Invisib-Burgess equation satisfies that property. We have half into A of u into u. So there, if we substitute A of u, we can split it into A plus and A minus. So G of u will be this, half into u plus half into u minus into u. So this will be G plus and this will be G minus. So we'll do backward differencing for this and forward differencing for this. So that way we obtain this finite volume update formula. So here we have backward differencing and here we have forward differencing. So now this is something that we have seen previously. Now let us see what happens if we go for some numerical schemes. So if you have, this is just a step function that I've shown here. Let's just call this as UL and this as UR. UL is just some constant number and UR is some other constant number. Don't confuse it with the UL and UR that we used earlier in the finite volume cells. So we constructed some cells and we called this to be L and this to be R. So this is nowhere relevant to that. I'm just putting this L and R just to identify the left and right side of this discontinuity. And UL is just some constant number, UR is some other constant number. Okay. So now you have this kind of initial condition. So how will this initial condition evolve now? So we told that previously for while doing PDEs we saw this, that when for Invisib-Burgess equation, when UL is less than UR, we'll get an expansion fan, and for when UL is greater than UR, we'll get a shock or come. So this is something shock, or we can call it as some discontinuity. It's not a physical shock, it's just some discontinuity, because we are only in the scalar case. Physically, when we want to call something as shock, then it will have to be dealing with Euler's equations, because that is only physical. So this is sort of a model equation, a tau equation or something like that, because it's a scalar equation, so which helps us to study most of the waves that occur in systems that like Euler's system. So this is just some tau equation to study all these waves. So when UL is less than UR, we'll get expansion fan, and on the other hand, we'll have a shock wave. So this is something we saw earlier. We drew the characteristics, and then through the characteristics, through how whether characteristics converge, we'll get shock, and if they diverge, we'll get expansion. These are certain things that we have seen earlier. So now here we have UL less than UR. So essentially this will lead to an expansion fan. Here characteristics will be diverging, and over time we'll get an expansion fan. So this will be our the actual solution. This is X. So our actual solution will be something like this, exact solution. So what will be the numerical solution here? So so suppose we have a point where this is 0, and here here we have some negative quantities, and this is all positive. We have some point exactly at the center, like here. This is u equals 0 point, and we also have u equals 0 here. Remember that for Burgess equation, dou g by dou u is also u. So we did the wave speed splitting and forward and backward difference thing based on the sign of u only. So here doing it with u is okay, but in complicated problems where dou g by dou u is not just a linear function of u, but some other nonlinear function of u, then you need to be looking at this value to make whatever the argument that I'm going to make now. So here it's okay to just look at u. Okay, I'll come back to that later. Okay, so now here you have this point u equals 0, and just by looking at the sign of dou g by dou u, we either go for forward or backward differential. I mean, we already had this equation, right? So depending on whenever dou g by dou u is positive, this only this part of the equation will be valid. This part will be 0 when dou g by dou u is greater than 0. This quantity will be 0, and this will only be considered. Similarly, when dou g by dou u is less than 0, this part will be 0, and this will have some value. So we switch between a forward and backward differentiating by looking at the sign of dou g by dou u. Although we have one full equation consisting of both forward and backward differentiating operators, when we do the computations, depending on the sign of dou g by dou u, either this will be on or this will be on. Both of them cannot be on together. So although we give the full equation, uh, while simulating, either this part will be considered or the remaining this and this part will be considered, depending on the sign of dou g by dou u. So here, you have dou g by dou u as u, and here we can see that there is a switch between signs at this point. So below this point, or to the left of this point, you have negative sign. Dou g by dou u is negative, and here we'll have forward differentiating, and towards the right we have dou g by dou u as positive, and here for these we'll be having backward differentiating. Okay, so essentially the scheme itself gets modified right at this point. So what will happen? How will the results be? Now I'm just removing all these things. So because of this reason, you'll have something, some glitch kind of thing in your result. So to the left of this, you'll be going somewhere, something like this, and to the right, at this region, you'll experience some kind of glitch. So this is commonly known as the sonic glitch. Okay, this happens at regions where there is a switch in sign. I mean, where there is a switch in sign of dou g by dou u, and hence there is a switch in the type of scheme that you're using. So you'll experience some kind of glitch over here. So this is commonly known as sonic glitch. So this is evident only in the expansion fan, because you can also see this face the same issue in compression region also. So when you have UL greater than UR, you'll only be having shock, and that will just keep moving. Okay, so here again, suppose if you have some point where your value of u is 0, here it's not you won't see it evidently in the numerical solutions, but here again there is a switch in the algorithm, because it's a compression region. Things go like this, things get compressed. So over here, so you won't evidently look at feel the glitch, know the presence of glitch there. But here, since things are expanding at this about this point, you will evidently see the glitch in the numerical solutions. So this is known as the sonic glitch. So any doubts?
So how do you deal with the glitch numerically?
Okay, actually, as of now, you can develop more methods to deal with the continuity of this dou g by dou u. we'll be seeing a method called Van Leer's flux vector splitting method, which solves this problem of glitch. Glitch is essentially not a big problem. You can have it, but if you really want to avoid it, you need to maintain this continuity of variables. This transition must be smooth. It is, you are doing some transition between schemes, right? You make sure that that transition is smooth over there, so that you avoid this glitch. So we'll be seeing a method, this Van Leer's flux vector splitting method, which avoids this glitch. We'll see the conditions that he has given to avoid this glitch. Yeah. Okay. Any other questions?
No, ma'am.
Okay. So we'll see, before going to Van Leer's splitting method, we'll see another method called Steger-Warming flux vector splitting method. Actually, this is the basic method. This is one of the first methods in upwinding. So this has this sonic glitch, but Van Leer's flux vector splitting method avoids this sonic glitch. So as of now, the current method that we'll be seeing will have this glitch. Okay, for systems of conservation laws, you see, we have this system known as system consisting of the conserved variable u and the flux vector g of u. So for now, let us do it for Euler's system only. Previously, we saw how to do it for any general system with u being any conserved variable vector. Here, let us just consider it to be an Euler system where first equation represents mass conservation, second equation, it is these two together will give us mass conservation. These two together will give us this equation. Because this equation with these first component of this equation is this mass conservation. And the second component of this equation is momentum conservation, and third component of the system is energy conservation. So now let us do the same procedure where we take the flux Jacobian, which is derivative of the flux vector. So A of u is dou g by dou u. So for this, uh, for Euler's system, this property holds. I've told you, right, we require this property k into A of u into u. So this property is required to do upwinding. For Euler's system, this property holds. In fact, for Euler's system, this k is 1. So we have this thing, because this can be seen directly. We know what g of u is, and we know what a of u will be. By differentiating g with respect to u, we can find out a of u. That is actually this matrix. So we can multiply this matrix with the conserved variable vector u and see for ourselves that it will be g of u. Okay, this property holds. So now for this matrix A of u, let us find out the linearly independent eigenvectors, and then let's diagonalize this matrix. So for that, I've not gone through all the procedures, but I've just written out the eigenvectors. So this vector is r1, r2, this is r2, and this is r3. So these are linearly independent eigenvectors, 1 u minus a and h minus ua. This is a vector, first linearly independent eigenvector, and r2 is the second linearly independent eigenvector, and third r3 is the third one. So all three, when I told you earlier that R is a matrix consisting of linearly independent eigenvectors as its columns. So R is such a matrix, and since these columns are linearly independent, you can always have R inverse. So you can find R inverse by using this. So this way you now have a matrix consisting of eigenvectors and an inverse of that matrix. So because we have linearly independent eigenvectors, So, you have a matrix, A of u equals dou g by dou u. So, for this matrix, if we try to find out the eigenvalues, those will be these, u minus a, u and u plus a. And these eigenvalues are real and distinct unless a is 0. Unless a is 0, they are going to be distinct. So, and these are physical variables, they are real. So, since they are real and distinct, we'll always have linearly independent eigenvectors. So, there's a proof for that. Okay, we'll always have linearly independent eigenvectors because of this reason. So, this matrix A of u can always be diagonalized. So, we can diagonalize them, and the diagonal matrix will consist of lambda 1, lambda 2 and lambda 3 as its diagonal elements. So, let us do Courant splitting. So, here we can split this lambda I as lambda I plus and lambda I minus. So, that way we are putting all the positive quantities in one matrix and negative quantities in the other matrix. That thereby we'll get D. We can split D as D plus and D minus. These are all okay. These are all certain things that we have seen earlier. So by this splitting, we can go about splitting of A actually, because A is R inverse, and D can be split up into D plus and D minus. Thereby we can split A into A plus and A minus. So that is something I've done over here. And since G is A into U, we can split G as G plus and G minus. So I've just written A as uh, R into D plus D inverse. Sorry, it's D minus actually. So A is R inverse, and we can substitute D as D plus and D minus, and then we can split these equations and split this expression. So thereby we get two expressions, one consisting of only positive quantity and the other consisting of only negative quantity. So we have G as G plus and G minus. So this is one thing. So suppose in a numerical, we can do this splitting and go about doing the finite volume update thing, substituting this expression in the using this expression to find the interface flux value at the interface, and then we can substitute that in the finite volume update formula, and then we can go about solving the system and find the solution. This requires so much of matrix multiplications, right? We require first we need to find D from A, and then we need to find R and R inverse as well. Then we need to, after splitting D as D plus and D minus, we need to split A as A plus and A minus. Then we need to split G as G plus and G minus. Then again we need to combine them all to find, here we require so much of multiplication. After finding D plus and D minus, we need to do this multiplication to find G plus and G minus. This requires too much of computational power. On the other hand, we have a simple way to do it, which is, U can be written as some summation. We can solve this equation. Consider these two equations. U as sum of alpha I into Ri, where Ri are these eigenvectors, R1, R2 and R3. And alpha I are some variables. We need to solve for alpha I using these two expressions. U as this and G as this. G as summation of alpha I into lambda I into Ri. So if we solve these two equations, we can find alpha I. These are solvable, and we can find alpha I from these expressions. So you can try those as an exercise. So once you find alpha I, these are going to be some variables only, scalars. So you only do a scalar multiplication over here. So after you find alpha I, finding G plus and G minus doesn't require any more matrix multiplication thing. You can just do this. You have this Ri vector, and alpha and lambda I plus are going to be just scalars. Although those are variables, they are just still scalars. You can just do scalar multiplication and then find this quantity. Here the computational power will be less compared to this matrix multiplication thing. So this whole algorithm can be carried out in this way as well, provided you find out alpha i's that satisfy these two equations. Okay. Yeah, this is Steger-Warming flux vector splitting method, but we have more arguments to do. Yeah. So now let us look at the supersonic flows. So for just a minute, I'll charge the laptop. Excuse me. So we have done Steger-Warming flux vector splitting as of now. So let us look at it more further. Like we have supersonic flow, and which is towards right. So for supersonic flows, mod u will always be greater than a. That is, modulus of your flow, magnitude of your flow velocity will always be greater than sound speed. So in that case, am I audible?
Yes, ma'am. Yes.
Okay, fine. So, your magnitude of flow velocity will always be greater than sound speed in case of supersonic flows. So let us just consider supersonic flow towards right. So where u is greater than 0. So in that case all the three eigenvalues will always be greater than 0. So when u is greater than 0, your and u is greater than a. So in case of supersonic flows towards right, u will be greater than a, and your lambda 1, which is u minus a, will always be greater than 0 because u is greater than a, and your lambda 2, which is u, will also be greater than 0 because for flow towards right, u is greater than 0, and for your third eigenvalue, u plus a, that will also be greater than 0 because both u and a are greater than 0. So all the three eigenvalues are positive. So here d will be completely equal to d plus and d minus will be 0. So similarly, if you look at supersonic flows towards left, your magnitude of flow velocity will be greater than 0. So mod u will be greater than 0 and u will be less than 0. So lambda 1, which is u minus a, will be less than 0 because u, which is a negative quantity, is use a negative quantity, and a, we have a minus a over there. We are just adding two negative quantities, so that will be less than 0. And lambda 2, which is u, and because it's a flow towards left, you have u to be less than 0, so your second eigenvalue is also less than 0. And your third eigenvalue, which is u plus a, is also less than 0 because your u is a negative quantity, and that negative quantity is bigger than the magnitude of that negative quantity is bigger than a. So minus will dominate and you will have a negative quantity. I mean, your third eigenvalue will also be negative. So that way the whole of your d will be equal to d minus, and in this case d plus is 0. So for for complete supersonic flows, in some physical domain, in some parts of the physical domain, if you consider certain problems in some part of the physical domain, your problem will be supersonic, and in some other regions they may be subsonic. But if you consider problems which are everywhere supersonic, then in that case you will either be doing forward differencing or backward differencing in space depending on your flow direction. So in that case, flux vector splitting is really not required. You can just, if you know that your flow is going to be supersonic everywhere in the domain, and you depending on the sign of your flow direction, that is depending on your flow direction, the sign of the flow velocity, or depending on the flow direction, you can take either forward differencing or backward differencing in this expression. Okay. So this is for supersonic flows. Now let us look at subsonic flows. So for subsonic flows towards right, in the first case, u is greater than 0. So for flow towards right, u will be greater than 0, and for subsonic flows, u is less than a. So the first eigenvalue, which is u minus a, will be negative, because u is u is less than a. So the negative u minus a is like some small positive quantity minus some large large positive quantity. So u is small and a is large, so u minus a is going to be negative, and since the flow is towards right, u is going to be positive, and u plus a, since both are positive, here u plus a will be positive. Since both u and a are positive, u plus a is positive, so you can now split d into d plus and d minus. So here d plus will consist of 0, lambda 2 and lambda 3 as its diagonal elements, and d minus will consist of lambda 1, 0 and 0 as its diagonal elements. So this way you have done flux vector splitting for subsonic flows towards right. Similarly, for subsonic flows towards left, you will be having mod u to be less than a, and u is less than 0 since flow is towards left. So in this case, first two eigenvalues will be negative and the third one will be positive. So here you have split d as d plus and d minus. So d plus consists of 0, 0 and lambda 3, and d minus consists of lambda 1, lambda 2 and 0. So this way we have done flux vector splitting. So we have seen that for flux vector splitting is not required for supersonic flows, and it's required for sonic flows. So at sonic points where we require some change, where m is 0, when Mach number is 0, it means that your flow velocity is 0, and when Mach number is plus or minus 1, you're changing from subsonic to supersonic things. When Mach number is plus or minus 1, you have a shift between subsonic and supersonic. These are considered to be sonic points. Physically, we only call this as sonic point. We don't call this to be sonic point. Here we call this to be sonic point because this also will sometimes cause problems like sonic glitches. So we just add this also to be, consider this also to be a sonic point here. So these are the places where we have a change in eigenvalues. So at m equals 0 and at m equals plus or minus 1, our eigenvalues will experience some change. Change in sign actually. So this change in sign will lead to a sudden change in the way forward differencing or backward differencing is done for that corresponding eigenvalue. So this is what that causes sonic glitches, this change in eigenvalues. We saw it in a simple way for scalar conservation laws earlier. For systems of conservation laws, these are the sonic points, and these are the places. When u is 0, obviously this thing is going to change sign. When u is 0, your u is changing sign from positive to negative or from negative to positive. So this lambda 2 is going to change sign. So similarly, when m is plus or minus 1, your u by a, when m is plus or minus 1, you're actually changing from subsonic to supersonic actually. So all three eigenvalues will essentially experience at least one of those. I mean, if you look at subsonic and supersonic flows towards right, uh, the first eigenvalue is different. So this will experience a change in sign. So in that case, anyways, we are going to shift the method. Because the method that we use is dependent on all the eigenvalues. Because G plus and G minus will have contributions, G plus and G minus have this D plus and D minus. So this matrix D plus and D minus changes when subsonic and supersonic flow change. When m is plus or minus 1 and when m is 0, this matrix D plus and D minus that we have, D plus is different for subsonic flows and D plus is different for supersonic flows. D plus is actually D for supersonic flows, and for subsonic flows it's different. So these quantities G plus and G minus will differ because RD plus R inverse U and RD minus R inverse U will change when you move from when there is a change in, when you are at these points, you'll have a change in G plus and G minus, and that will result in a change of the scheme. So this will lead to formation of sonic glitches. So this is essentially Steger and Warming flux vector splitting method. So here split flux vectors G plus and G minus are not continuous functions of Mach number, and this causes sonic glitches. And also it's a first order upwind method. Yeah, it's a first order upwind method, right? You have done first order backward differentiating and first order forward differentiating. You have not done second order things. All are first order operations. So you get a first order method. So any doubts here? Any doubts?
No, ma'am, I don't know.
Okay, fine. So shall we go to Van Leer's flux vector splitting method? So now that Steger and Warming is over, we can look at Van Leer's flux vector splitting method, which avoids sonic glitches by putting some conditions. Okay. So can we look at it now?
I don't mind, ma'am, if others are also okay, you can continue.
Okay.
Yeah, we can
Yes,
start.
ma'am.
Others, is it okay?
Yes, ma'am.
Yes, ma'am.
Fine. Yeah. So you have finished, we have completed this Steger and Warming flux vector splitting method. So that causes sonic glitches. We have seen all that. So now let us move on to Van Leer's flux vector splitting method. So we in this method we put certain that is Van Leer puts certain conditions to avoid the sonic glitches. He makes sure that things are continuous. Actually, initially I told that the problem occurs because G plus and G minus are not continuous functions of Mach number. Van Leer ensures that G plus and G minus are continuous functions of Mach number, thereby he avoids sonic glitches. For that, to make them as continuous functions of Mach number, he also we cannot just directly make it as a continuous function of Mach number. When we do some modifications, all other things will get modified. So we should make sure that all the properties of upwind scheme finite volume method are not affected while doing this modification. So for that he has put some conditions. So those are Van Leer's conditions. So first observation is, first thing is G of u. We have split the flux vector G of u into G plus and G minus. This was there in Van Leer, Steger and Warming flux vector splitting method. Here he made G to be G is a function of u, right? That is u was rho u and rho e. So G was rho u p plus rho u squared and pu plus rho u. So all of these can be written in terms of these. Like suppose if we take this as u1, this as u2, and this as u3, the first element is u2, and the second element can be written as some function of u1, u2, and u3. Similarly, the third one. We have seen this during PDE classes, I guess. We have seen these explicit expressions as well. So let's not go into those details. So it's just that g of u, each element in g vector can be written as some function of u1, u2, and u3. So this is what we did in Steger and Warming's flux vector splitting method. What Van Leer does is he considers another vector. Instead of u, he takes another vector v bar consisting of row a and m, because he wants g to be a continuous function of Mach number, and which is influenced by a. He is taking this vector instead of the actual conserved variable vector. So he just considers this vector now. So now he is splitting this g. Anyway, g is going to remain the same. That is, instead of writing g as rho u p plus rho u squared and pu plus rho u e, he'll be now writing these in terms of rho a and m. That is, first element rho u will now be written as some function of rho a m instead of rho u. That is, u is now Mach number is u by a, right? So u is now rho a m. So rho u will become rho a m in terms of Van Leer's fluxes. So his first element is rho a m instead of rho u. Both are actually same, just the way he writes is different. He writes them in terms of rho a and m instead of rho u and e. So he just changes that because he wants them to be continuous functions of these quantities, essentially Mach number. So this is first property. The next one is the eigenvalue, that is the vector. First, what we did in the previous case, we had dou g by dou u, which this was our matrix A of u, and this had eigenvalues, right? And we split those eigenvalues, dou g plus by dou u and dou g minus by dou u, and dou g plus by dou u had all positive and zero eigenvalues, whereas dou g minus by dou u had negative and zero eigenvalues. It is the diagonal elements of d plus and d minus were either here was just positive and zero, and in this case was just negative and zero. So what Van Leer does is he makes sure, because these properties of upwinding must not be affected, so he wants his eigenvalue, that is for his matrices dou g plus by dou v bar and dou g minus by dou v bar, those matrices must also have eigenvalues greater than or equal to 0 and less than or equal to 0 respectively. So this is another condition. So now these are two conditions. The next one is g plus or minus must be continuous with m. So continuous functions of Mach number. So g equals for supersonic flows we had this condition. G equals even there in the previous case for supersonic flows, whenever Mach number is greater than 1, g is completely equal to g plus and g minus in this case was 0. Whereas in this case, g is completely equal to g minus and g plus was 0. So this was the supersonic flows condition. So he makes sure that in his framework also the same holds. And also he wants to mimic the symmetry of g. This g plus and g minus together wants to mimic the symmetry of g. What does it mean is the following. So here g is rho u p plus rho u squared and pu plus rho u e. So this is g as a function of u. Here g is written as a function of v bar. So in terms of rho a and m. So the same function is written as a function of v bar now. So we can see that each of these elements are now, first one is a function of rho A and M, but here I've written only in terms of M. Okay, I've not considered the degrees in terms of rho and A. I've only considered the degrees in terms of M. So all of these are functions of actually rho A and M only. But here in this place I've just written only in terms of M because I'm more interested in what power of M they are in. So first one, G1 is a function of M and G2 is a function of M squared and G3 is a function of M cube and M. Okay, so these are certain inferences. So now from this we can see that since G1 is a function of M, G1 of minus M will give us minus G1 of M. And since G2 is a function of M squared, G2 of minus M will give us G2 of M. This is an even function. And since G3 is a function of M cube and M, both are odd, G3 of minus M will give us minus G3 of M. So this is some observation from the form of G. So these are some observations. So what he does is he makes sure that G1 plus and G1 minus also follow the same thing. That is, G actually follows these things. The whole G actually follows these properties. This is what we saw from the form of G. Now he makes sure that G plus and G minus that he constructs also follows the same properties. G1 plus of minus M must be equal to minus G1 minus of M and so on. So he ensures that these properties are satisfied as well. So now and then he also makes sure that dou G plus or minus by dou V bar must be continuous. The derivatives must be continuous. Initially we got this the sonic glitch because of that discontinuity problem, because there was a sudden shift between G plus and G minus. We got into problems of sonic glitches. To avoid that, he ensures that the shift is continuous. So he makes sure that dou G plus or minus dou V bar must be continuous. He puts that as one condition. Next is he makes sure dou G plus or minus by dou V bar, this is actually V bar, must have one of its eigenvalues vanish for mod m less than 1. For mod m less than 1 means subsonic flows with Mach number between minus 1 and 1. So we saw previously, right? The subsonic flow case, this one. For flow towards right, one eigenvalue is negative and the other two are positive. For flow towards left, two are negative and one is positive. It's like for either of the directions, one of the eigenvalues has different sign from the other two. That is some inference for subsonic flows, and he puts that as one condition. That is, his eigenvalues for his flux Jacobian matrix must also have the eigenvalues vanish. One of the eigenvalues actually for this thing subsonic flows. This since one of them are different from the other, either of these have one of the must have one eigenvalues, at least one of the eigenvalues to vanish. It is in D plus, at least there should be 1 0 and two not and the other remaining non-zero quantities. In D minus also we must have at least one non-zero quantities. If all three have the same sign, then all three elements here will be non-zero. But since at least one of them have different sign from the others, so D plus and D minus will have at least one zero element. So he wants in both the cases, it will have at least one zero element in the diagonal. So that's what he says here. This must have one of its eigenvalues vanish, that is become 0. At least one of the eigenvalues of this matrix, that is positive and negative matrix, this must go to 0 for subsonic flows. By looking at what happens in Steger-Warming, he puts more conditions on his own scheme, and he obtains a scheme that satisfies all these conditions. Okay. Additionally, to have, to avoid so many glitches, he has put an additional condition, a different one. So to have continuity, if we have polynomial of the same degree, it's not possible. We must have some polynomial of higher degree to have continuity. We saw g1 was a function of m, so he makes g1 plus and minus to be function of m squared. And he saw g2 to be function of m squared, and he makes them to be functions of m cube. And g3 as function of m cube and m, and he makes g3 plus or minus to be functions of m power 4. So, since we already have this, if we make g1 plus and g2 minus also to be function of m, we'll surely get a discontinuity. So in order to avoid that discontinuity, he makes his polynomials to be of 1 degree higher. Okay, now these are some conditions. So with these conditions, let us see how he derives his expressions for g1 plus and g1 minus. We already have the finite volume update formula. What the method does is, the finite volume update formula is actually the same. And the way we are going to write I plus half n is going to be the same. It's just going to be gi plus gi minus 1. Similarly, gi minus half at n will be I minus 1 plus g. So these are the same things. The only difference is the way we evaluate gi plus and gi minus, the way these things are evaluated. Initially, for Steger-Warming flux vector splitting method, we went through the eigenvalues approach and we diagonalized the dou g by dou u matrix, and then we split the diagonal matrix into d plus and d minus, and then we obtained g plus and g minus by using this homogeneity property. It is g of u equals a of u into u property. We obtain g plus and g minus through all that. Here, the only all of them stays the same, except that the way we evaluate g plus and g minus are going to be different for Van Leer's flux vector splitting method. So here he uses, the conditions that we have put until now follows. So g plus is a function of g1 plus is a function of m squared, g2 plus or minus is a function of m cube, and g3 plus or minus is a function of m power 4. So g1 plus, let's now obtain an expression for g1 plus and g1 minus. So g1 plus will be a1 m squared plus b1 m plus c1, since it's a function of the highest degree must be m squared. So we have a quadratic polynomial in m for g1 plus. Now we need to find out a1, b1 and c1 using the observations, using the conditions that Van Leer has put now. Using all his conditions that he has put, we will be evaluating a1, b1 and c1. So, for Mach number less than or equal to minus 1, we want g1 plus to be 0. For Mach number less than or equal to minus 1, this is supersonic flow towards left. So in this case, you want g1 plus to be 0 and g1 minus to be g1. And for Mach number greater than or equal to 1, which is supersonic flow towards right, you want g1 plus to be g1 and g1 minus to be 0. That is your condition, right? Your third condition. So he uses that condition over here. Okay, so that condition is being used here. So since we are now evaluating only g1 plus, we don't care about g1 minus as of now. Let us now just look at g1 plus. So for Mach number less than or equal to minus 1, g1 plus is 0. And for Mach number greater than or equal to 1, g1 plus is rho um. So since this holds for all Mach numbers greater than or equal to 1, we can evaluate the value for g1 plus at m equals 1. So that will be just rho u. And at m equals minus 1, we told about continuity, right? We wanted our flux G1 plus and G1 minus to be continuous functions of Mach number. So for m less than or equal to -1, G1 plus is 0. And G1 plus is continuous with respect to m. So dg1 plus by dm exists everywhere. And for this value of dg1, for g1 plus equals 0, which is a constant number, dg1 plus by dm is going to be 0 only. And since everywhere, and since we assume that g1 plus is continuous with respect to m, you want a smooth variation. You put this assumption that at m equals -1, this quantity exists. At m equals -1, you put the assumption that derivative. No, it's not an assumption. You are putting a condition that your derivative exists at m equals -1 to enable smooth variation with respect to m. This is to avoid sonic glitch. This is exactly where you are avoiding sonic glitch. So initially, we had a drastic variation at this point at m equals -1, G1 plus was not varying smoothly. It was drastically changing. So in that case, dg1 plus by dm won't exist when there is a sudden change. But here, when you assume that dg1 plus by dm exists, then you're assuming a smooth variation. So this puts a condition that smooth variation happens. So here, and that here this assumption dg1 plus by dm exists gives us smooth variation. But the value equals 0 comes from here only. G1 plus is 0 and G1 plus for all m less than or equal to -1, and dg1 plus by dm is 0 everywhere for all m less than or equal to -1. So that gives us equal to 0 condition. So now from this condition you derive. So we assume the form of G1 plus to be A1 m squared plus B1 m plus C1. You get dG1 plus by dm as you differentiate that G1 plus with this expression with respect to m, and you get this expression. So from this you put the 2A1 m plus B1 equals 0 is what you obtain, and from in this if you substitute m equals -1, you are going to get B1 equals 2A1. So this is one form, that is you obtained a relation between B1 and A1. So now what remains is C1. So now substitute this expression in your old G1 plus. So G1 plus becomes A1 m squared plus 2A1 m plus C1. So now, at m equals -1, what will you have? Put in this expression for G1 plus, you substitute m equals -1, so you're getting something like this. And you already know that G1 plus is 0 at m equals -1. For all m less than or equal to -1, your G1 plus is 0. And and you substitute the value for G1 plus at m equals -1, and you get a condition that C1 equals A1. So you get such a G1. You have obtained a relation between all three quantities. So all three variables A1, B1 and C1 can be written in terms of A1 itself now. So G1 plus is this expression. So now the only thing is you need to evaluate A1 from this. So now for that you could use the other condition. For m greater than or equal to 1, we had these two conditions, right, for supersonic flow conditions. We are using essentially these two conditions to do everything. So for m greater than or equal to 1, we have G1 plus to be rho am. So now for this in this expression, you substitute this G1 plus equals rho am for m greater than or equal to 1. And since it holds for m greater than or equal to 1, it holds for m equals 1 as well. So you substitute m equals 1 in this expression. So you will get A1 plus 2A1 plus A1 equals rho A. Okay, and thereby you are getting an expression for A1 which is rho A by 4. So now you have found an expression for G1 plus, which is this. A simplified form of that is this one. rho a by 4 into m plus 1 the whole square. So with similar arguments, we can get g1 minus as minus rho a by 4 into m minus 1 the whole square. So this way we are getting the expressions for g1 plus and g1 minus using the conditions that Van Leer has put, and using he has followed certain upwinding conditions that are already there in Steger-Warming flux vector splitting method, and also he has put some additional conditions to avoid the sonic glitches, that is to avoid discontinuities. So we are getting two expressions. Now let us look at it pictorially. What have we actually done over here? So we know that g1 plus plus g1 minus is going to be g1. This is actually the same that we have seen from earlier on, and for even for this Van Leer's conditions, it holds. The condition g1 plus plus g1 minus equals g1 holds. So let's look at it first pictorially. Before that, we'll make this thing, a small variable change. G1 is rho am, okay, and G1. Let's consider another variable G1 tilde, which is G1 by rho a, which is going to be m. G1 tilde will be equal to m. This change in variable is actually done to get a 45-degree line over here. If we have this rho a as a coefficient, then we won't be getting a 45-degree line. Instead, we'll be getting a different line of some other angle. Since we need a nice picture to understand what's happening clearly, we are doing this variable change. And similarly, G1 tilde plus will become G1 plus by rho a, and G1 tilde minus will become G1 minus by rho a. These two quantities, they'll be we are obtaining G1 tilde plus and G1 tilde minus from these two quantities. Okay, now let us plot these things. M in the x-axis and G1 in the y-axis, and G1 tilde is now the 45-degree line that we have obtained. So now what will be G1 tilde plus and G1 tilde minus? So this blue thing is our G1 tilde plus, and this green curve is the G1 tilde minus. So these two curves now satisfy this addition. G1 tilde for m equals in this region, that is these are supersonic regions, right? In supersonic regions, here we want G1 tilde plus to be completely equal to this is flow towards left. So G1 tilde must be completely equal to G1 tilde minus. So that's what is happening. In this region, G1 tilde is plus is 0 and G1 tilde minus is exactly G1. Okay, to the left, this left of minus 1. And to the right of right of 1 here again, we want G1 tilde to be equal to G1 tilde plus, and G1 tilde minus should be equal to 0. So that's what we have. This G1 tilde minus, this green line is 0, and this G1 tilde minus is exactly overlapping with G1 tilde. In the middle, what we have is this. We have a smooth variation. What we would initially have in in the Steger-Warming case is this. I'll draw this Steger-Warming case over here. So this was just a straight line for Steger-Warming. We just had 3 straight lines. That is, this is one straight line, this is one straight line, and this is one straight line. For Van Leer, what has happened is, instead of these two lines are still the same, but instead of this straight line, we have a smooth variation. It has become a curve. Since
Instead of being linear, it has become quadratic over here. So that's the only difference. Because we wanted to have smoothness, we assumed 1 degree higher, function of m squared. So that assumption helped us to overcome this discontinuity. So that way, here we get a smooth variation. You can see this over here. Our G1 plus is smooth. G1 minus is also smooth. So if we add G1 plus and G1 minus over in this region, we'll get G1. These are both symmetric, right? So this will adding these two will give us G1. So this way we overcome the sonic glitches. Similarly, this is all for the first component of the flux vector. Flux vector has three components, G1, G2 and G3, and we have done splitting only for the first component. And we have obtained the expressions by using the conditions. Similarly, by using the conditions for G2 and G3, we can obtain G2 plus and G2 minus. Similarly, G3 plus and G3 minus. So that way we get this picture for G2. For G2, this white line is G2, this white curve over here. And this blue one is G2 plus and the green one is G2 minus. I have drawn it non-smooth in a non-smooth manner, but it's actually a smooth variation. This thing is quadratic. G2 is quadratic, whereas G2 plus and G2 minus are cubic. So you ensure discontinuity here. You ensure smoothness over here. Okay, similarly, you do it for G3 as well. You split the fluxes by making sure that all the conditions are satisfied, especially the smoothness condition and the other upwind conditions like supersonic necessary conditions and subsonic conditions. If all of those are satisfied, then you get different fluxes, that is split fluxes that allow smooth variation. Okay, and these are the split flux vectors of Van Leer's. So yeah, this is G1 plus and G1 minus, and here this plus or minus we have over here. I've written both G plus and G minus in the same expression. So just this change will lead us to plus or minus G. So these are all for G1 plus and G1 minus. This way we get the split fluxes. So these split fluxes will ensure, these split fluxes are for subsonic flow conditions. For supersonic flow conditions, we already know that these will be the conditions. That is, G1 plus will always be G and G minus will always be G. That is for supersonic flow towards right, G will be completely G plus, and for supersonic flow towards left, G will be completely G minus. These will be the expressions for supersonic flow. For subsonic flow, you will be having these things. So you will be using these to enable smooth variation. To have smooth variation. So the consequences of using these conditions and observations are the following. We don't have sonic glitches, and we get less diffusion compared to Steger-Warming flux vector splitting. So we have not yet argued about how diffusion gets reduced in Van Leer's flux vector splitting compared to Steger-Warming flux vector splitting. Yeah. So any doubts here?
No, ma'am.
Okay, fine. So we'll stop at this point. We'll meet probably next week. Yeah. You can always ask me if you have doubts. Contact me. Okay. So no doubts, right, as of now?
No, ma'am. We'll all just go through the set.
Yeah. Okay, then we'll stop here. Okay, fine. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Bye.